all, it means that, as I learned, there are people from power electronics and computation, so I might do something less understandable. So please ask questions. That's the point. So please ask questions whenever you are in doubt, and I will try to be pedagogical if possible. We focus on those problems in grids, in electrical grids, which can be solved by means of control. So not necessarily would be interesting from telecommunication point of view. Nonetheless, looking at those algorithms, perhaps you will see where communication with a specific quality of services would be necessary, where it is not necessary. And more or less the problem is the size of the object, that it's a huge optimization object where we are fighting against data by sending as little as possible and trying to extract information from little piece of chunk of information to make a reasonable control, whereas you would kind of make a technique to compress in some other ways, and so we try to solve the same problem of a huge amount of information, but in a different way, and perhaps this is a time to join our efforts. So this is a motivation, and motivation is kind of Danish. So we have this ambition of having 50% of renewable energy, specifically wind. You probably were outside this morning and you noticed that it's relatively windy, so it's a good idea to have many wind turbines here. Nonetheless, there are problems. So you think that wind turbines are, renewable and all that, but there are counterintuitive problems. And this is a representation more or less what is the counterintuitive problem. So you can in principle predict wind profile. You have some partial differential equation with profile of the terrain and so on, meteorological data that you can predict relatively good wind data. And out of this wind data, you have certain coefficients from wind turbines, some aerodynamic coefficients, and you can actually compute relatively nicely power coefficients, how much power you can extract from the wind. Nonetheless, there are tiny mistakes. So you can see this is predicted in the state-of-the-art, this green one, state-of-the-art predictor, and the blue one is the true one. So you can see, there are those small errors. And these small errors, you could think they do not mean anything at all. No, they do mean pretty a lot. And then I will stop for a while. This is one problem, and I will catch up on this a bit later. And another problem. The red curve provides information of the consumption in Denmark. So you can see that we are pretty effective workers during the daytime, during the nighttime we sleep, and during the weekends we are lazy bastards and we do nothing, and also almost no consumption. But the wind doesn't comply with what we want. It's this correlation between consumption and the wind is relatively different. So from time to time we have deficit of energy, like here, and from time to time we have actually too much of wind power. And what it means, you should imagine that someone has to cover those differences. So someone has to stop production here, someone has to produce much more here. For that you have power plants, big power plants. And power plants you cannot just switch off. They are in a dwell kind of mode, like your car is on a dwell mode that you can turn your gear and then you drive quickly. So you see, another problem. So one was that those small pipes won't be able to cover because power station will run. So where you think that you will save on ordinary traditional coal-driven, oil-driven power plants, you won't do this because someone has to run on standby. So there is one problem. And here, these spikes. I agree that the errors were very small. So here is the actual power and here is predicted. So this is illustration what was happening. So error is relatively small, that's true. Nonetheless, the time shift, small time shift between curves exists. In other words, there will be a huge spike from time to time. Someone has to cover those. So difference at this point, of course, is small, but here will be small. So idea is that there will be spikes of lacking or excess of energy for a very short time, which we have to in some way to cover. And we mentioned that power plants, it's not the solution. So who should react? The consumption should react. So we should control consumption instead of production. Nonetheless, always problems. Nonetheless, if you start increasing consumption and start to control the production, start to increasing solar panels in your grid, you will have again problems. You could have under voltages, you can have over voltages, you can have increased load. In other words, your grid is not prepared for that. Your grid is prepared that power flow is from the high voltage down to our houses. But suddenly you produce voltage or you produce power at the very bottom, and flow goes the other way around. So, still problems. This slide represents how complicated is the system, and for power electronics it's clear, but for me it was more like shocking. This represents a small piece of a town, small tiny town of 20,000 in Brønderslev, which is 30 kilometers north from Aalborg. And then I asked them, well, could you zoom upon my street? And they, oh, it's too big, you don't want this, but a bit of this street. And I got this picture, where my house is somewhere here. Goodness me, it's very complicated, and I'm going to control all of those consumption in each house. So the system is humongous. Another problem. If the system is humongous, what would be the most naive or intuitive way of solving? Let us aggregate those. Let us aggregate together and not control like one house at a time, but maybe 20, 30, 100 houses. And then you aggregate and you look like curve like this, and you see, all right, there is some pattern, some kind of several sinus factions which are composed together. And then you look at each of the houses, split them again, and you see, well, they are completely different. One is, you can see the pattern in this consumption and that consumption is very different. That means you cannot control that one and think that this controller could be just naively split to this one and to that one, because they are doing completely different things. And then consumption, where another subject would be, well, to find flexibilities. So for example, a refrigeration system doesn't have to be turned on all the time. It has some inertia. In other words, I'm interested to keep my milk in between 2 and 3 degrees, but whether it's 2 or 3, I don't care. Someone in between. That means there is a flexibility. I can, switch it off when it's 2 degrees, and I have still 20 minutes of not using electricity until the temperature increases to 3 degrees. But there are dangerous situations. One dangerous situation is you can think, I will use it in my ham, which is in the freezer. And then if you do it like this, it appears that the small ice cubes in the meat, they will increase. So food will be like eatable, but it won't be any pleasure to eat it. So there are dangerous situations also there. And then you look at the curves, and suddenly there's one curve, and there's the other curve, and then you realize, what are those peaks? And then you realize that each refrigeration system have defrost cycles. Defrost cycle, it's a time when you remove build-up ice. So when you have your refrigeration system also at home, you can see that there might be some layer of ice on the evaporators. And this has to be removed every day because it's isolation. And it's removed by heating up, that it's melt down, and then it's done. And those are the energy peaks when you melt down the ice. And this doesn't matter when you do this. Whether you do it during night or day, it doesn't completely matter. So those are those flexibilities. So big job of smart grids, people are identifying where are the flexibilities that nobody cares where those are, just that they happen from time to time. And this gives you flexible consumption. Another problem, so voltage control. So imagine that there is a radial, so there is a transformer, and here are some agriculture, houses, and so on, and here will be some kind of solar panel installed. In the morning, there's a lot of sun, and the voltage increases. So this transformer and the voltage has to be kept on a certain level. So when it's on a certain level, you have to change the windings of your transformer by so-called online tap changers. And you do this once. Then again, there is a lot of sun. Voltage increases. You do it twice, and you do it several times. Then there are some clouds, like in Denmark, around 3 o'clock, and then there is not so nice weather, and everything, the voltage decreases, and then there is no sun at all because it's evening, and then you have to again change your tap changes to the right level because voltage level is too low. And you can say there is a nice controller who does it, apart from that this requires some mechanical changes. In other words, if you do it twice, first of all, there are very few of those which are applied. It's very expensive piece of hardware. If you have enough money and have those tap changers, then another problem is that they can change only a couple of times during a day, 2, 3, that's max. Here we had 5, 9 tap changes. It's way too much. And why it happened? It happened because someone installed solar panels. So you like them, that they introduce, renewable energies, but people who take care of voltages, they hate them. So, okay, so this is maybe not so important. Of course, everyone will have maybe electrical vehicle instead of its own traditional vehicle, which we could use storage in cars, but this you already know, so I won't elaborate on this. And in Denmark we have electricity grid, and we have to balance in between consumption and production at all time. We are so lucky in Denmark that we have a strong connection with Norway and we have strong connection with Germany. So if we do something silly, nothing happens really. But still, it's expensive to use those connections. So now I will go more toward theories, control type of techniques, what we actually use to tackle some of those problems. And here is one of the problems. So there is someone who has a portfolio of different consumers, of different renewables, of different power plants, of different maybe factories, and has to kind of use as little money to run in this system, and at the same compensate for balancing. So you have one objective. So it sounds like optimization. So it sounds optimization we are doing here because we have to earn as much money as possible on this, and at the same time keep the balancing. So in other words, if it happened that production, let us say from time to time in Denmark actually price of electricity is negative. Very seldom, but there is. In other words, my optimization will say stop producing, but you may not stop because you have to have constraint. You are committed to have a balance at all times. And for that, I allow myself to kind of, since I knew that not all of you are from the same background, allow myself to tell a bit about optimization and see how we tackle the problem. So this is kind of maybe partly PhD course, so I may allow myself to put some equations, I hope. But it won't be like undergraduate, some of those things. So, but only to have a feeling what we are actually working with. It doesn't matter that when I say optimization and I say how we solve it, that I will in principle solve it in this way. Because one thing is, mathematical formulation, and the other thing is how you make algorithms that are numerically sound. So a lot of story I will not, which is below the seawater level, I will not discuss it. But problem is, again, earn as much money as possible, keeping balance at the same time, and maybe keeping voltage levels in between one voltage level and the other voltage level. So you can see, it's always, we are talking about problem, it's one of the formulations that we want to minimize a certain function subject to constraints, which are equality constraints and inequality constraints. And for that, you probably, doesn't matter if you had or you didn't have, in your undergraduate courses, you introduce Lagrange multipliers. You introduce Lagrange multipliers both for equalities and for inequalities, and instead of, you solve that problem. So you don't no longer look at f function alone, but rather as an extended function which has new variables, Lagrange multipliers for inequality and equalities, and your state. And how do you actually solve this problem? So you solve it in two steps. First, you say that, all right, let us keep alpha, lambda, and v to two Lagrange multipliers. You think about those as, maybe I will give you an intuition. You can think about, maybe this is the best intuition you can get. You can think about, there's some agreement. So this you can think about balancing. So if it's 0, it's perfect balancing. If it's non-zero, there is no balancing. So V's and lambdas as well, it means a shadow price. It means price. How much I will pay that they do not agree. This is more or less what it means. So this is a price I introduce. Apart from my optimization, I optimize price of not agreeing. So this is a price, and this is, if it's 0, so I'm agreeing. If it's not 0, then we are not agreeing. You can define a function which is dependent only on lambda and v, and it's getting from this L function. It's called Lagrangian function from before. It's this function, where it's found infimum over all your states x. So you can use gradient searching methods, whatever algorithm you have. If it's convex function, so just okay, there is an infimum, I take this point, but it changes. Depending on price, right? Think about that. You produce something, and depending on the price, you will produce more of it or less of it. And this is the same. I give you the price, and you give me the price, and I will tell you how much I will produce of it. And this function, for what, and the optimum of the previous problem, the first problem, the true problem we started with, is always greater or equal to this claim with different prices and different production compliant to the prices. What it means that now, if I take the most favorable price, so apart from those prices you gave me, there will be one which is most favorable that I will earn all in all most money, right? There must be some price. And if I find this price, then this function for that price and that function will be equal. So what I'm saying, that solving this problem is the following situation. You give me a price, I tell you how much I will produce. Then among your prices, I will pick one which I earn most, and this will be precisely the solution of the optimization, constraint optimization problem we started with that one. So this is a kind of short crash course on optimization, how you actually solve those type of optimization. Of course, there are some assumptions. I don't know, you probably started to look at this smart grids literature, and you see always, well, constraints are linear, they are polyhedral, functions are convex, everything is convex. It's because this algorithm works only if everything is convex. If it's not convex, then optimization and this best earning for me with this price idea, there will be a gap. But if it's convex, it's exactly the same object. And now we have to move it maybe a bit here. So let us take an example that we have a function we have to optimize with respect to some equality. So this is some kind of matrix linear operator, and we have to optimize only among those x's which satisfy these equalities. So how do you do this? So one thing is beautiful theory, which I described before. You take textbooks, and the other thing is how you make algorithms. There are two different things, and this is maybe very important. So in reality, you don't use Lagrange multipliers here. I'm sorry. I can't figure out what this is for. Now we can see it. So in reality, with Lagrange multipliers, you can only solve nicely numerically. You can only solve equalities, which are in smart is less important. Oh, they are important because balancing is there. But inequalities, they are very hard to solve. And instead of solving inequalities, what we do, we produce some kind of tricks. So you can imagine that if we have some function and I'm going to optimize it only on some set, then I can build some kind of boundaries here and introduce another function which has extremely huge values on the boundaries, such that, and it's 0, I mean, it's not continuous function, doesn't work, but in the ideal situation, I can introduce function which is 0, where I'm interested to find a solution, and on the boundary it grows like hell. And then you can see that if I'm interested in finding minimum, this will be such a big thing that I will never consider something which is in this side or in that side. So the concept is like the following. We define function which is infinite big outside. It is 0 on the set. We sum this new function with our objective function and optimize in ordinary way. And this, it's an ugly trick, but it's one which works numerically. So, for example, to give to persuade you. So, if we want to minimize x in between these two inequalities. That means these two inequalities define an interval between -1 and 1. So if we want to optimize x in between -1 to 1, I know that it's trivial, it's 1. Oh, it's minimum, so it's -1. But just to see what is happening, then I define a function which is 0 in the interval from -1 to 1, and it's huge, infinite. I mean, infinity you cannot implement in a computer. In a computer it will be 10 to the plus 10,000 or something, right? Outside. So it's 0 here, and otherwise it's very huge. Alright. This algorithm, so what I'm saying about it, because there is a huge variety of optimization algorithm which makes, one thing is again theory, and the other thing is what is numerically stable. And it appears then instead of, so if we have minimization with subject to equalities, so I proposed you before to use, when we do not agree, we have to pay by shadow price these Lagrange multipliers and study this, this problem as we said. You give me price, I give you how much I will produce. But it's not very stable, numerically. It's much more stable if you introduce quadratic term as well. So you have Lagrange multipliers for the linear term and Lagrange multipliers for the quadratic term. So here is a price that we do agree in linear sense, and this is price that we do not agree in quadratic terms. And it appears that these algorithms, and I mean, it's strange because it's very, I think it's 5 years old or something, and it's so natural to introduce it. And I think there's algorithm which is not so important, and then you can see how you use it. So you have minimization of a certain linear function. I took just to have some intuition, subject to quadratic constraints. So this would be like an ellipse. We can make the Lagrangian type of approach with prices. That means we introduce a term which is price of disagreement. We can also use the augmented one where we introduce also the price of quadratic disagreement. And you can see the situation. So this will be like pure Lagrangian technique, how convergence goes, and then for this example you can see that this quadratic is much more smooth and quicker, much quicker convergence. So this is just to say to you that there are different techniques. Alright, this is just a start of it. So there is some kind of, so you can see in the slides later on, or textbook, or even a wiki, I think on this level it's enough how it works. But there is some catch. The catch is that we optimize centrally. If I have millions of different consumers and and producers, I have to get all this information up, and there is some big optimization procedure which runs, and then communication to each of those. Come on, this simply doesn't work. So we were focusing in control departments, not only here, but all over Europe and maybe United States as well, on making distributed optimization. Well, how we can optimize it in the distributed way, especially for smart grids. And especially for smart grids, there is the following problem statement. So you can see this is very much presentation of a control person. So we have, and you will see like statement of the technical problem, physical problem, mechanical, electrical, heart surgery problem. We convert it into piece of formal statements, and we forget what it is for a while. We just want to say formalization of the problem for your specific problem. For smart grid, specific problem is of the following size matter. We have a production or cost of production in one unit, cost of production in the second unit. Let us take only 2 units in the beginning. But they both contribute to balancing the grid. That means sum of production should be constant. We have to balance. But price I earn on this and on that, in sum, it would be something I would like to either minimize, or if it's price, it's maximize. If it's cost, I would like to minimize. Depends. But this would be the typical problem. And beautiful situation is that the x's for one plant and z's for the other one are decoupled. Why not using this structure for something? And this is precisely what we were focusing in control. It's not because there is something below it; it just stops such an abrupt way. I think I will better look at this one. So we have again optimization. So we have optimization. So this was what I should supposed to find minimum of. And there was part which comes from quadratic disagreement, and this part from linear disagreement with prices lambda and rho. To understand the concept, we don't look We don't need to look at this part. I regret now that I actually put it. But see, if I optimize, I have two variables. I have a variable x and z. If I optimize with respect to x, well, this function is not dependent of z. Why should I, to find the minimum, why should I take it into account at all? In Lagrange multipliers, there is also this agreement dependent on z. Why should I take it in account if it's dependent on z alone, if I optimize with respect to x? That means, if I'm standing here, I have one plant and there is another plant. I don't need to know what you are doing. I can do it independently. And there is more. So what should we do? So the same situation will be with respect to z variables. And in conclusion, I can optimize separately for x, separately on z, but there is a small catch. That lambdas are common. So what it means? There will be some kind of central algorithm which will set up price, but if you send price to me, I can optimize with respect to this price. If you send the same price to me, I can optimize the same price. So this will be like an algorithm. There will be central, very simple algorithm which sets up price, and there will be local algorithm which optimize with respect to this given price. And you can see where it comes from. You can see those control people, they are usually not very wise, but they are good at stealing ideas. And this idea comes from economy. So in economists, they had this problem, how to beat big enterprises that every small department, they actually fight for the good. But at the same time, they should think about company. And this is exactly what is happening, that company sets up internal prices of exchange of information, and then locally each department can optimize its production. But it's very, very important to set up the right price. So I think this will be like a general description of optimization. And again, it's central because all these smart grids from control person, it's about optimization. Minimum price with respect to keeping voltage constraints, with respect to keeping frequency on the right level, so with some constraints, whether equality or inequalities. It's always the same story. And then let us come back to this example I had, that I have a portfolio, I'm a portfolio which wants to earn most money on that portfolio, and in my portfolio I have power plant, I have central heating power station, I have consumers, I have renewable, and I want to earn as much money on this, but at the same time I want to make a balance of the energy. And again, there are some notions which kind of, when do you say, and I use them interchangeably, but it's actually a bit wrong. I use interchangeably notion of energy and power. So when we in this field talk about power, we actually always referring to frequency, keeping frequency on the right level. When we talk about energy, so we think preparing someone to take over. So for example, power plant, if I need you to participate, I cannot just turn you on. I have to do some, I have to burn more oil or coal or whatever. It takes time, this process takes time. That means it's no longer nanoseconds, microseconds or whatever. We are now talking about seconds, up to minutes for some plants. And if it's longer than instantaneous, it's energy we're talking about. So that's why by purpose I was talking about here more energy, but at the same time you will have a concept of in the same situation you can also study power. But it means that, for example, for power station, what you will use, they have some tanks of a there's inertia, for example, in your power plant, so you can use this to something. There are some extra steam you can use. You know, you have steam in stored steam, and then you can use just steam to accelerate your generators. So there are some tricks how to do this very quickly, not necessarily using this slow process of burning something. Okay, but here I would like to show, that's the first technical, the last technical maybe slides. So I will show you how we actually use it. So for this specific case, so we want to minimize energy. Everyone wants to contribute to a given power, so I trade on the market that I want to produce C, and then everyone has to produce the C, but I don't know who should produce how much. And this optimization should tell me how much each of those should produce, such that all in all I earn most money as a greedy person. And of course, what do? We use dual decomposition. So we have, again, maybe it's not so important to look at this, but we have local optimization. So you give me a price, I optimize my axis, that is production, such that I earn most money. And of course, this is money I really earn, and this is the money I pay because we do not agree. We don't have perfect balance here. We have to all pay for it at the very end. But someone has to compute this price, and there is another algorithm which minimizes a certain function g, but this is finding the right price. So there are two algorithms. Local algorithm for each of those consumers, producers, and there will be like a central unit who will optimize, give you the right price. Why I'm saying this? See, so sometimes we think, each of us think separately, like, what should we, how should we, you know, someone gives you an optimization and then you would like to make with your communication network this working. But sometimes solution is an algorithm that you split up heavy algorithms to be done locally, and slower algorithm to be performed globally. And then information, it's only piece of information we have to send forth and back is the price, nothing more. See? So there are different ways of attacking the problem of things being huge. And this is sketch of a bit of the situation. So here it's an electrical grid with these gray lines. These are both consumers and producers, and this is the telecommunication connection. So there's some two graphs. One which is defining telecommunication connections, and one which is defining the grid connections. And this is maybe because only those are very near each other, or maybe some other reason. So if the graph is connected, the algorithm will work. More connection, the algorithm will converge quicker. This is the point. So if you telecommunication people can afford to make more connections, our algorithm will work quicker. And of course, all connections should be done, because if this doesn't have information about the price, it won't work. And here, if it all works, and it doesn't work because we have another system now. This I will not present, but there was a curve presenting how they agree upon the prices. And you can use it for different purposes. So here you have more piece of this city I live in, so it's not on one street, but 5 streets. It's still huge. Huge. All of those are end users. All those are end users. So it's huge. Each of those will have their own solar panels, vehicles, you name it. And then maybe it's less important now, but you have to state constraints for each problem you have within smart grids. You have to state what are your constraints and what you would like to optimize. So here, for example, you would like to have, just to give you some constraints. So in an equality constraint would be, you would like to charge your car within some time cheap. So you give, I have 10 hours to charge my car, and it's up to you how would you like to schedule your charging. So one constraint would be like that. But your charging, you can only use, and you can discharge if grid wants it. But the problem is that you can only discharge enough energy, and there is some limit on discharge energy, and there's limits how much energy you can put in your batteries. So there are some limits as well. Also, how much power you can put into your battery before it burns. There are some other limits. So all those limits you have to put into your optimization, and you guess it's going to be huge. There are some limits upon voltage on the grid, and all in all, you get huge optimization problems. So here it is minimum of loss energy, for example. So these are resistances, for example, currents. So how much energy you lose in your cables, and then provided you have to keep your voltage on the reasonable level. You have to charge your car. You have to yes, the other one I didn't describe so accurately. So this is it. So bottom line is like that. That this optimization technique. So this is one thing. Then there are some algorithms which you also have to take care that it's very huge optimization. That's, for example, dual optimization is solving that one. And then you have to solve technical problems, try to convert it. So all those technical, voltages, currents, limits on currents, time of charging batteries, everything has to be put as constraints in your optimization. And then you run it. The problem is that it's so huge that it doesn't work. And maybe we should switch camera when I say doesn't work, because we say that it does work. But it doesn't work. It does work in some cases. So if you start aggregated the units together and deal with this as a one system, it kind of works. But if you really want to tackle all of those systems separately, it won't work. It's simply too big. And I will show you now in the second part of the talk, which takes much less than the first part of the talk, because time is kind of running. I will show you another way of looking at the situation. How to use probability theory instead of, so we, again, control people, we are not kind of like a special technique. If optimization solved it, we do optimization. If probability solved it, we do probability. If homology solved it, we do homology. I mean, we are shopping around like and optimization doesn't solve, so we don't have no bad feelings. We wasted 5 years. Come on, we go another way. So now we go another way. So first of all, we should have a view upon that there are some of consumption are flexible and some are not flexible. For example, bulbs. You could take all million people are talking about those millions of bulbs. Let us turn them and save some energy on those. No, because maybe you can save making better bulbs, but not when I turn it. When it's 6 o'clock and I want to read my paper, I want to watch TV, I want to prepare food for my kids, I have to turn on things. So there are flexible and unflexible, and it looks like there are some peaks of this unflexible consumption. There are peaks in the morning when you go to work, and kids go to school, and in the evening, of course. On the other hand, there are small refrigeration systems. In each so I talked before about finding out flexibility. So one part of this business is finding flexibilities. And let us look at the refrigeration system, how it works. So we have refrigeration system which does the following. If the temperature is low, I switch it off. Temperature grows. When it's too high, I turn the compressor on. Temperature falls, up and down, up and down. But the temperature moves in between those regions. And this supposed to be 310 degrees, or maybe 5 degrees. But actually, how I schedule this, it doesn't matter. It's because Delphos mounted their favorite equipment in this, thermostat in this, that's why it looks like that. But who said that I shouldn't do like that? Turn it a bit frequent in some time and almost very seldom in some other periods of time and so on. Just I keep temperature in between units. This means that there are flexibility. Here I don't use electricity, here I use much more electricity. It means that inertia of a refrigeration, this is a small refrigeration, but bigger even more, I can use to something. I can use it to shift consumption from here to some other place. But one thing is sure, that if I don't consume here, there will be a lot of consumption just after. What if we take thousands of small refrigeration? Can we deal with this? Think about this communication. And if I look at the numbers, the interesting thing is that these are it's more clear for power engineering people what primary and secondary reserve are. Primary, so it's more like frequency control, it's abrupt, it's now, it's at that time, and the secondary, it's more like, it takes some time for preparation of usage. And you can see in Denmark how much it is. Roughly 59 megawatts, and secondary is bigger, it's 181 megawatts. If we combine all small freezers, refrigerators, we can actually have 93 megawatts. So we don't need this if we can use those refrigerators. If we additionally use heat pumps, and electric water heaters, then we have such a huge number. So there is a lot of potential in heat pumps, all those thermodynamical equipment we have in houses. The problem is to control those. And what we want that all of those will kind of be aggregated to one huge system which can follow some kind of references. So if the power is growing, I should be able to control all my refrigerations in the country to follow some kind of curves. And you can see, that's not really possible. So what we did, we took a small refrigeration, we experimented a bit, we produced first a schematic model of it, how it works with refrigeration, with dampers, evaporators, blah, blah, blah. We produced, after some years of work, we produced two differential, stochastic differential equations describing how it behaves, and it behaves differently when it's turned on, it behaves differently when it's turned on, because in one temperature is growing, in the other one is falling down. And, well, it's only for one refrigeration system. What do we do then? Well, we use optimization. At this time we were still very focused on optimization. It will work, we say. So we formulated the problem and solved like I described to you. And then we tried and we sweating like hell. And what we get? That we can only optimize 20 refrigerations. Ta-da! And it breaks. We use state-of-the-art optimizers, everything, help us, MIT, Caltech, help us, give us better. 20, full stop. You cannot do it better. It worked. Alright, optimization worked. But only 20. What should we do? Alright. Then we had very wise PhD student, Lunita, and she said, what if we take as a large number? In large number, if they are a big enough number, they will maybe behave like one. And this is precisely what we did. So we combined all refrigeration system into one big chunk. We measured how much power they use, and we wanted to control them with one signal. With one signal everywhere. Every refrigeration system in Denmark should be controlled with one single signal. What do you think? Cool. And see, this is the story, how we did it. So I will just advertise a bit for probability. So we took these stochastic differential equations, and of course, if you want to study stochastic differential equation, you can only study the realizations, right? And realization doesn't say much. So it would be much better to have a probability density function that someone is turn on or turn off. And there is, since there are Markov processes, so there is a way of converting it into partial differential equations, so-called Kolmogorov or Fokker-Planck equations. So we simply converted it with standard theory. As I said, we shop around, so suddenly, all right, in my shelf, I have kind of functional analysis, I have geometry, and suddenly, woo, stochastic assistant the last 5 years, new investments. And then, all right, we solve it with partial differential equations, these Fokker-Planck equations. The problem is that they are partial differential. That means they are infinite dimensional. In control, I don't know in your field, but in control, controlling infinite dimensional system is a very difficult task. So it has to be some kind of approximation, good approximation for that. And we studied different solvers of partial differential equation. You have final element technique, but there's some catch that this technique should preserve probability density functions. So not that suddenly you integrate and you get something which is bigger than 1 or smaller than 1. You have to have technique which preserves it. And then we figure out a technique called final volume technique. It does have this preservation. So we studied final volume technique in numeric solution to get it. And in short, we had these two differential equations, a partial differential equation, which we converted into two probability density functions. One which says what is the probability the temperature is some interval and the thermostat or the compressor is turned off, and the other the same, but with thermostat is turned off. And there are actually so this is just to formulate. This is standard. This is what we found from textbooks. This is the standard Fokker-Planck equation, and then of course it has to be converted because we have two differential equations. We've switched between those, so we kind of converted. Suddenly we have two differential equations with some tricky boundary conditions. Not important at all, equations are not important, but the graphs are maybe more important. So at a given time, at a given time, we have probability density functions. So for example, so of course everything is dynamic, it's not static. This picture is given for second number 10, let us say. And then there are those two functions. Probability density function 0 and 1. 0 says that at this time, a temperature interval, the probability is that one. If it's then off, and this one is saying that, for example, at this temperature interval, probability will be here. So in other words, if I integrate over those curves or graphs, I will have the probability that the refrigeration is on. And if I integrate over the other one, this is the probability that refrigeration is on. So suddenly I don't want to control really turning on and off, but rather probabilities that it will be turned on and will be turned off. And this is more clearly the story how we did it. So again, stochastic differential equation, Fokker-Planck equation, which is partial differential. This is not a matrix. This is a partial differential operator. So, infinite dimensional system. We use these numerical methods to find a discrete, space discrete version of it, and that's it. So this is the end of story of modeling. So what models provides? Models do provide something else. It provides just a point. So probability in discrete points of the temperature of refrigeration system being off or being on. So this we can compute. This is a bit about how technique works, and this is a bit important graph. It is animation, but it doesn't work. I apologize for that. But you can, if you download my slides, so you can click on it and you will see. But this is computed probability density functions methods. And this is actually one which is taken from, if we have 100 refrigeration system and see what is the temperature. So we simulated actually a realization of 100 refrigeration systems. And see, well, there are some discrepancies, because they are only 100, but if you increase the number, and I can't recall what was the number, maybe 10,000, it's almost there. So really, the law of big numbers works here. So we cannot control if we have very few, then we can use optimization, but if we have a huge number of objects, suddenly we are controlling, we are able to control. And you know, there's always catch. There's always catch. And the catch is that all those refrigeration systems should be relatively homogeneous. That means they should be similar to each other. So you cannot just take a small refrigeration here and big here. You have to combine small to small, big to big. And this is the curve which presents it. So the blue one is the truth. So this is this probability distribution function, how it evolves in time. Simulated is almost the same if they are homogeneous. But if now the refrigeration systems start to be different, and you can see how much they deviate by standard deviation or something. More they deviate, bigger. So this is one deviation. This is even bigger deviation. So more you deviate, less accurate is your model. So there's the catch that those systems you should have in your portfolio, they should be more or less identical. They should be very, very similar, or very just similar. I think I'm approaching, right?
So 12, 15 is
okay. So how do we control it? Now it's a bit interesting. This was just a model, and how we do control it? Intuitively, what would we do? What would we do? If this is probability density function of turning on, and I want to switch it off, I would like to decrease it. At some point, pull it down a bit, right? Decrease it. And of course, if I decrease probability density function of turning it on, I should increase that one, because probability of turning on and off is 1. So sum of area below that and sum of area between this plus this should be the same. But how to realize this thing? This is just wishful thinking that I would like to decrease it. And in equation, so you can also this silly idea you can actually put into the equation. So for example, I will not go through all of those equations. Maybe only say here. So this is a probability density function of the refrigeration's whole population, which is off because it's 0. And then I would like to I would like to switch some portion, epsilon 0 portion of those, I would like to switch it off. That means I change probability density function, I swap it from those which are on to those which are off. So you can see, these were on, but because I switch it off, they move to the situation that they are off. Yeah, mathematically it kind of works. I didn't cheat or there's no problem at all. Nonetheless, how to realize this thing? And here is implementation, how we do this. Okay, imagine that we are more than here. We are maybe 10 times more. And I ask 1/6 of you to stand up. Because we have a question, we have the following question. We have the question that I epsilon was the portion of your population. This is what my control parameter. So how to say that portion of you should stand up? How should I realize this? Well, I can give you a dice. And I can say, for example, if I need 6 of you standing up, I can agree with you. If you got 1, you stand up. And precisely, if you are many of you, 1/6 of you will stand up. So 1 parameters I sent to this, and because of law of large number, precisely in average, 1/6 of you stand up. So again, we should know whether population is, we are talking about population which is off or on, and then we have a Bernoulli trial which is turning the dice. And if you have 1, you turn off. If you have 2, 3, 4, 5, 6, you turn off. That's the only algorithm. Very, very, very simple algorithm. And again, this works. So this, again, this curve represents reference. There are two curves on this. One is which is reference, and the other is what actually population of refrigerations do. And of course, I won't present it if it wasn't any positive result. So we are following the reference. Nonetheless, if there is a big discrepancy between sizes of refrigeration system, really big, you can get a curve like that. That means being non-homogeneous. That means that the refrigeration system, you take like a big refrigeration from supermarket and compare with your tiny refrigeration system. This won't work. Again, sometimes, and why we present it, because sometimes control has these robustness properties that if you put things in a closed loop, it starts working. But here, even in the closed loop, it doesn't work. They have to be relatively homogeneous. Maybe very last slide. I have very last slide, which presents what is. This is very much for control nerds. So how it looks like. So for others, maybe does mean a bit less. So this is these are the states. States are the probabilities of the temperature being in some small intervals, and it's cut into small intervals. All temperature from 0 to 5 degrees is covered by small intervals. So this is the state. Then there is some linear matrix. This linear matrix is humongous. It's very big. But it has, so for those working with numerical method, but it has this property that it has most of the components or entries are on the diagonal, and then there are some tiny information outside. So all of those are zeros. So my matrix is big, but a lot of information is only on diagonal and a bit symmetrically out of diagonal. So if you build algorithms, it should be taken into account. Then there is a linearly entering a matrix which is dependent on this epsilon parameters. This epsilon parameters, how big part of your population should be switched off, and state again. C times F, it means pick only those which are on and multiply by how much power they use. They are all almost identical, so it's the same power coefficient, and this means what is the power of the whole population. So just for the nerds, how this, and this is control. So control problem would be follow the reference where control signal is epsilon. Just for that. And I think this was very last slide I had, and that's it. I'm happy to answer questions.
At the beginning of the presentation, one slide 7, you disregarded the aggregation. You consider that it was not feasible. It was not. But later on, you are talking about aggregating more.
Yeah.
So it's different from...
Yeah. So I was thinking about aggregation will work if you don't have too many. Aggregation will work if you have not too many components, not like 20 to 100, because then in aggregation you could use a ordinary optimization. But here I had many. This is also aggregation. So this is also aggregation, but really many. So this is a story about what I do when aggregation is small, and what do I do when aggregation is huge. The number of elements in the population.
So you are not you don't disagree with the this kind of service provider that it is called aggregator?
No, not at all. Not at all. I even more agree that suddenly we provide business cases for them. Yeah. Because someone who has to invest in telecommunication infrastructure, in the optimization algorithm, and I suddenly provide them a way of earning money, because there will be them who set up shadow prices. So they will run the shadow prices algorithm, deliver to each of people participating in this aggregation, and they will optimize accordingly. I don't disagree with aggregation also.
I thought that you were...
No, it was...
DC-based optimization, and you said there are connections within the grid and also communication connections. And did you study the impact of the communications on the convergence of your
Yes.
algorithms? So did you have some model for communications, or did
Yeah, there is a model, very, very primitive model, which says maximum delay time. So we have a certain, we study in time of convergence, and this time of convergence will depend on how much information there are and also on delays. And we have a simple model for that, relatively simple model. So only the worst case. There's no probabilistic effect included, only the worst case.
And a related question, so in the optimization, as far as I read the literature, basically you need just the averages. So you need to know the state of all the entities in the power grid network. You basically just need to know the average of certain parameter or signal in order to do control.
But this is more like philosophical question. So let me say like this. So reality, if we want to make a reality, modern reality, that's not possible, right? Because there are always some details we have to discard as kind of noise. And first you have a question. So there's no notion of modeling without having what kind of question, what we would like to answer. And then you take a model which answers this particular question. And if they had a question which is, I would like to do it in average, then average models are all right. But if you want to suddenly cover those small peaks, which happens very seldom, these models won't work. So you have to make more accurate models. So it's mostly depends on your question. And also our models, even for optimization, will be very, very different whether we like to control a frequency or voltages or even energy. For frequency, for example, we won't control with optimization, and power people here will probably agree with me that it won't work. It's too slow. You have to react quickly. You have to react on the frequency signal. If it goes down, you should put more power into it. And how we do this? We adopt the idea from power engineers who use Druck control. But Druck control has this advantage that it doesn't have integral action. That means there will be always an offset. And in order to remove this small offset, we have a slow optimization controller which asks all those components and tells how to remove this small offset. But it works very, very slowly. So we have very quick frequency control, which does exactly the same as old systems, plus we have slower controller which removes the offset. So again, for this we have to have very accurate model. But again, we ask only questions about frequency. So it's not covering all. And even studying the grid, the radials, you make some aggregation, make some assumption anyway. So it depends on the question once again. Yeah?
I'll go back a bit to the model of the bridges that you had with the on-off switch state. So the thing with bridges and other similar appliances and the power electronics, their lifespan depends on how many times you switch them on and off.
Mm-hmm.
So when I would compare your graphs, you had about twice as many switches, which means about 30% less lifespan. I agree with you, and this was our consideration. So this was the more pedagogical version of it. There are also versions which takes into account how many switches we experience this. In other words, for example, one solution would be you shouldn't, if temperature is very, very low, you shouldn't switch off, because then you will have a lot of switching, and on the opposite scale will be the same situation. So there are some regions. If you notice, maybe I can show it just. I didn't talk about it, but if you notice, I divided into different regions. So I said here, don't do too much. here, don't do too much, here you can do whatever you want. And those two regions are there because switching were so often that it didn't make any sense for this appliance. So you are catching exactly the problem that we impose a lot of switches. But we also try to solve it. But of course there are more switching than normal. Of course.
And the other thing is that
But opposite, you will get money for this. You know, maybe lifetime is decreased 30%, let us say, I don't know how much, but electricity will be cheaper, so you will be able to pay for it. Right, for decreased lifetime. Maybe. I don't have numbers.
And based again on that switching, there's a limited time for each fridge until
Yes.
it needs to go up again.
Yes.
It depends on the state it was before.
That's true. That's we also, yeah.
From my calculation, on an average fridge right now, usually on the average, when you have thousands of units, you will get an average time of about 7.5 minutes only, which is not enough to do frequency control on the secondary level, which usually need at least 30 minutes. So how do you?
So okay, so you know, it depends which kind of controller you. That's also kind of how much intelligence you use in this. How much, you know, what kind of calculation. I'm not kind of 100 sure. I don't want to kind of cheat. The only thing I can give the graphs, which those maybe we can read minutes. How many? Oh, it's not minutes. It's for sure seconds. Oh, in minutes. So it looks like we can take 20 minutes.
20 minutes.
Yeah.
That means that you cycle through groups of fridges then.
Once again, sorry?
That means that you have different groups of fridges and you have every few minutes you
Oh,
use.
yeah, this was very ideal. So you have, you know, the number I now is gone, but you have really many. It's maybe unrealistic, maybe, you know, 100,000, and it doesn't make sense because, you know, half of those will be in East Denmark, some of those will be in West Denmark, and we have different problems. I agree, but you can use it. We had discussion, for example, with Fuji, where they say, but well, all of those vending machines we have in Japan, this is what you could use because we own actually those, or there is some owner of those, so you can implement it. This doesn't answer much of your question, but it is a long way between practical implementation of those, definitely. But in this study, I can see kind of not 20, it's more like 10 minutes. But of course, this is max. All those curves, this is max what we presented. After this, you cannot hold it any longer. That's max in these studies. And you are right that there are some. You have to take care of number of switching. You have to also take care of time in between switches. So you cannot just switch, you know, you switch now and just microsecond after you can switch off. No. There has to take some time. Of course.
Shall I?
Sure.
I have a question regarding the pricing. In the models, were you considering day-ahead prices?
So these particular studies do not have pricing, real pricing included. As it. And this has to be included in the following way that if you, so this was like all those studies were done that we take offline prices of 24 hours, how it behaves, right? But if you start to put it on, you have to have a prediction of pricing. And you also have the prediction how other will react, because if other react, price will drop. So we don't have this. And this is, there was a project in Bornholm when they made these studies, and it appeared to be a very big problem of unstable pricing, because, you know, suddenly price is low, everyone reacts, but now price goes up.
So when it gets closer to real time, do we really have the time to optimize and then control the units?
And that's why I talk about frequency control. That for some of those, no. For some of those, like today, you assign certain power station which will control, or big funds, wind funds, to control, will control the frequency, and it has to go quickly. It's nothing to do with online pricing. Online pricing is only for the energy questions, a bit longer in time. I don't believe it will be possible to make trading so quickly.
But then price was one of the parameters which defined the optimization, to reach the minimum.
That was not with the fridge.
No,
That wasn't for the fridge.
Not related to this, but the previous
The
slide.
previous one, well, but this was for energy. It wasn't any really.
That's for dynamic pricing in direct control. That is direct control. So you have indirect control for load shaping and direct control for frequency.
So you can yeah. So I call it shadow prices, but they were not true prices.
Yeah.
They were mathematical objects.
Yeah, so that's exactly the question. When it comes to reality, real prices in the market, how does it work in
Okay. So I won't answer accurately, but I will say what are our considerations. So we wanted to put wind turbines on market in the following way: that if wind turbine, if there is lack of power, we would like to go above rated. That means increase fatigue on the wind turbine. That means lifetime, or switch it off a bit, produce less if markets requires this. Well, putting it down and up, it's the problem is that you will have swinging of your structures correspondingly, and it costs of lifetime. It's maybe 1/3, 1/2 of the lifetime, and we wanted to put it into market perspective. And we were naively thinking, all right, we take 24 hours kind of prediction, and then we control according to this. But it wasn't any good. Because others react as well. So answer is that we don't have good things, but we are solutions, but we are working toward it, and we have a project where there are economists who actually make models, probability models of the pricing development dependent on wind flow, humidity, temperature, and such that you can know what will happen, then react accordingly. But the short answer is we don't have an answer for online or real-time market inclusion. That would be short answer.
But for forecasting prices, you can also assume that this is a technology, because there are like a lot of companies doing it. So it's probably not so much of a research question at the moment. For the forecast of prices, you can more or less consider it as an input. There are some companies doing it.
Okay.
Yeah, but there are companies also doing control, but the question is how well.
Yeah, and also the imbalance prices, it's absolutely unpredictable. In real time, the imbalance prices, you get to know after it happens. And I don't think there's a way yet to find out.
Anyway, those techniques, so there was this project, and all those techniques, these ad hoc techniques, naive techniques, they resulted in unstable pricing.
Yeah.
That you switch it off something, so they make an experiment that they switch something for small piece of a radial, and then suddenly prices started to oscillate, not for a short time, but a relatively long time. And I think this might be an open question, and there are in the literature very new articles which are dealing with that. But again, how to get the right model? Before starting, you have to have a right model. Of the, such a silly thing like clouds, when you have solar panels. Some people are opting for having a statistical market. That means you don't know what you actually earn or lose, mostly earn, but in average you know. That it's not like every time you know precise number, but in average that you do the right thing, because it's so uncertain. Probably won't happen. That this will be an implementation.
Okay, then. Thanks a lot.